Hi everyone, this is chapter 12 on global climate. It gives us a very good baseline before we talk about global climate change. So this is an analysis of what our climate is, and then it introduces two notations that will give you some ideas on how to study climate change. Let's get into it. If we look at climate types, we need to look at our climate like we did in the first chapter. Microclimates, small zones, a city park. Mesoclimates, a region like the Pine Barrens or the New Jersey Shore. Macroclimates are larger states. I'm thinking of states that have a region that is quite even in its climate, like Alabama, Wisconsin, or even an island like Great Britain. And then there's global climate. So we're going to look into this and get a feel for what we mean when we say climate change and quantify it a bit better. I'm going to be introducing these visuals to you. And so let's get into the fact that climate controls from our atmosphere impact our climate temperature and precipitation. These are the two main things we're thinking about in terms of climate. We're thinking about ambient temperatures, surface temperatures, and precipitation. When we talk about some of these climate controls for the global climate, we are talking about ways of looking at global temperature by isotherms, the easiest way for us to see that visually. And we're talking about looking at global precipitation in terms of pressure systems and in terms of topographical changes. So let's go back over this a bit more. When we look at temperatures globally, we'll be looking at longitudinal patterns for solar heating. We'll also be looking at where our isotherms bend in relation to the distribution of land and ocean and the impact of ocean currents. When we are talking about global precipitation, that's where air rises. And air can rise as a result of pressure systems or as a result of topographical changes. We've been studying what forces air to rise, and we know that when air rises, it undergoes expansional cooling and condensation, and that's where we find the precipitation. Let's go into that a little bit more succinctly and visually. Here's our isotherms globally for average annual sea level temps. And when we look at this, we see that the latitudes really reflect the solar heating intensity. When you think about the equator through this area, you're thinking about where the sun directly or most directly impacts the earth with its radiation. And then you see that while I might have the equator right around here, the warmest temperatures on Earth are really in the southern hemisphere. The reason for that is the land-sea distribution. There's more land in the northern hemisphere, there's more ocean and less land in the southern hemisphere. More ocean in the southern hemisphere means more convective flow to heat, so more even heating in this area. And more land in the northern hemisphere means that that land is going to lose and emit that heat at a faster rate. Remember our soil experiments. So you need to also keep in mind when you look at these isotherms that these are all temperatures that are corrected to sea level temperatures. Remember, we corrected sea level pressures that accounted for elevation? Well, we're accounting for elevation on sea level temperatures as well. For instance, you see the Himalayas here, but you don't see the temperatures up in the Himalayas that are below freezing. And you see the Rockies here, but you don't see the temperatures that are much colder up in the Rockies. The reason is because we correct those temperatures to a standard temperature lapse of approximately 6.5 degrees Celsius per 1,000 meters. If you think about Colorado and about 5,000 meters, you're talking about a 35-degree difference when we're correcting it for sea level temperatures. So that's very significant for that. But these climate controls that we're talking about, meaning the solar heating intensity by latitude and the land and sea distribution, impact the temperatures that our climate shows. In addition, and in correlation, ocean currents dramatically impact climate as well, and they impact climate through temperature as well. When we look at ocean isotherms, they tend to bend near coastlines. Look at the bend that you see here with the upwelling along the South American continent. Look at the bend that you see here with the isotherms caused by the Gulf Stream. These isotherms are bending near the coastline on account of the Coriolis effect. Remember, you're seeing a clockwise rotation in the northern hemisphere because the flow is moving to the right. And you're seeing a counterclockwise rotation in the southern hemisphere because the flow is moving to the left. So you're seeing the start of that flow for the temperature, but you're really seeing the temperature stay uniform with that flow because of the specific heat of water, which we addressed in one of our labs. So that water is going to maintain its temperature and lose temperature more slowly as it moves into those northern areas with the Gulf Stream. And this temperature is going to stay cooler as it moves toward the equator with the upwelling in the southern hemisphere. These ocean currents have a decided impact on our climate, especially in New Jersey along the coast. We know that temperature impacts pressure, and pressure systems are also a powerful climate control mechanism for our global climate. We know that temperature impacts pressure because when it's warm, we can create air that is less dense. And when it's cold, we can create air that has higher density. So just to review what we know about for our global circulations, we know that there are latitudes where air rises because it's so warm and less dense. And in those areas where air rises, that's where we tend to notice more precipitation. The temperatures are relatively warmer around the intertropical convergence zone, and that by the equator is an area with a lot of precipitation and rainforests. That impacts the climate. And conversely, we know that around the 60s degree latitudes is another area where relatively warm air, when we compare it to polar air, will rise and condense and precipitate. So this is an example, both of them at the equator and in the 60s, of expansional cooling and more precipitation. Conversely, in areas where air sinks, you notice compressional warming and drying. Those areas where air sinks are at our 30-degree marks where our global circulation tends to send it down as it's getting cooler up in the upper atmosphere. And as this air descends right in the 30s, we tend to notice that it will compressionally warm and dry out. So you are sitting on a lot of air that is coming down and causing a high pressure system, what's called a subsidence subtropical high, that has dry air. So remember, we talked about the horse latitudes. Very visual thing to remember. And you notice this subtropical high right here. You also notice this relatively cool air sinking at the poles as well. The world's deserts are known for being under these subtropical highs at the 30-degree mark, and there are deserts at the poles for the same reason. So when we talk about what's happening now with our weather during the winter, this subtropical high that's normally right around Jacksonville, Florida, is moving south a little bit, because remember, the sun is really concentrating on the southern hemisphere at this point. And as a result of that, we are getting really impacted by the precipitation from the relatively warmer air that is rising in response to the polar fronts that are heading down from Canada. So that brings our wet winters that we're seeing now. These pressure systems also impact our prevailing winds. So when we look at that, this is a very recent December 2nd notation of prevailing winds at 500 millibars, an upper level wind, and isotherms at sea level at 1,000 millibars. So the isotherms are the colored ones, and you're seeing that around New Jersey. We're getting in some cool air from Canada. It's moving down. You see that for isotherms. When you look at the prevailing winds, that is where you can start to see the pressure gradient forces take effect. And those pressure gradient forces, as we know, move from high pressure to low pressure. So what you're noticing here is that the high pressure is coming down from the polar regions and is pushing down in here, and you see the temperatures coming with it. And it's pushing into the low pressure regions that are more toward the equator. You have a high pressure area from the 30s that is moving down around here, and you're seeing that it is stopping the descent of the cooler air. That high pressure area is moved right around here, and it is just stopping the movement of that air so that it turns right around and moves right away. So pretty interesting to see that high pressure area moving that prevailing wind from high pressure to low pressure. These prevailing winds impact our climate in a macro area, in a macro climate around our region, and in a global area. In areas where there are big topographical changes, especially out on the West Coast where there are mountain chains, you notice climate controls in those areas due to forced topographical lift. And that forced topographical lift is coming in right off the ocean. And as it comes in and expansionally cools, it drops its water on what will become basically a rainforest. These are the redwood forests of California along this first ridge in from the Pacific Ocean. But on the other side, that's where you're noticing the fires, because these are very dry leeward hillsides. This will happen over and over again. You actually get in over the Sacramento Valley. There's more water evaporated out of the Sacramento River that prepares this area here for a rainforest right in Yosemite.